let us try to solve this problem. So what is asking, for the network shown in the figure, the zero sequence reactances in per unit are indicated. The zero sequence driving point reactance of node 3 is. So zero sequence driving point reactance, what he is asking you to calculate the Thevenin's equivalent zero sequence reactance between node 3 and the reference. Reference is ground for the zero sequence networks. Okay, all the indicated reactances values are zero sequence reactances only. All the indicated reactants are zero sequence reactances only. Okay. Now, what is the first element? First element is the generator. First element is the generator, which is whose neutral is solidly grounded. Whose neutral is solidly grounded, and he has given xg0. That means it is equal to our zg0 value. Next, there is a transformer. This transformer primary is delta connected, secondary is star connected and solidly grounded, and the zero sequence, the reactance of the equivalent reactance of the transformer is 0.15 per unit. Next, there is a transmission line whose zero sequence reactance is given. Next to that, there is one more generator which is also star connected and whose neutral is solidly grounded. Here the zero sequence reactance of this generator is 0. Okay, so there are only 4 elements present here. So first, if you draw the first element, what is the zero sequence impedance of the alternator or a synchronous machine? It is Zg0. So here it is 3Zn, this is ground, and this is Zg0. Okay, now you can see here Zn, in what way the star point is grounded? It is solidly grounded, so the neutral grounding impedance is 0. So this value will become how much? This value will become 0, and Zg0 value is directly has given J0.1 per unit. Okay, the next element is transformer. How is the primary connected? Primary is delta connected, so series switch is open, shunt switch is closed. Shunt switch is closed. Again, you have the impedance. How much? J0.15. Secondary side, how it is connected? Star and grounded. So series switch is closed with 3 times the neutral grounding impedance. Here neutral grounding impedance of the star side of the transformer is 0. So it is 3 into 0. Next, you have transmission line whose per unit reactance is J0.05. Directly has given the zero sequence reactance of the transmission line. Again you have generator. This is Zg0 of generator, and this is 3Zn. Okay, so 3Zn value is 3 into 0. Zg0 value is J0.2 per unit. So this is the all ground points we can connect. This is the zero sequence network of the given power system network. Now, where the bus 3 is located? Bus 3 is located after the transmission line. So bus 3 is here. This is bus 3. Now he's asking the equivalent impedance between bus 3 and reference. So bus 3 and reference Z0 equivalent. Thevenin's zero sequence impedance is how much? That is the question. So if you take this one, here we need not consider this portion because it is open. So here this is one parallel path and this is one more parallel path. So it will become J0.2 per unit in parallel with J0.2, which will become J0.1 per unit is the equivalent zero sequence Thevenin's impedance. So what is the right option? Option C is the right option. Option C is the right option. Understand? First we have drawn the zero sequence network for the given power system. Again, between the node 3 and the reference, we have computed the Thevenin's equivalent impedance. Same question. Now you try to do this and tell the answer. First, which element is present? Tell me, first element is what? Alternator. The zero sequence impedance of alternator is 0.03. This alternator is star point is grounded through a resistor which is 0.25 per unit resistor. Okay. So first, if I draw the zero sequence network for this alternator, it will become what? It is 3 times the resistance, that is 3 Rn. It is 3 into 0.25, the resistor value, so many per unit, and then the reactance value is how much? This reactance value is J 0.03. Understand? So this is your Zg naught, this is your 3Zn values. Okay. Next, what is the element that is connected to this first alternator? There is a transformer whose primary is delta connected. So primary is delta connected means what you have to do? You have to keep the series switch open and you have to close the shunt switch. So series switch open, shunt switch is closed. Again, the equivalent reactance of the transformer, which is given as J 0.1. J 0.1. Okay. Now, how is the secondary side connected? Secondary side is star connected and solidly grounded. So I have to close the series switch with 3 times the neutral grounding impedance, which is 0. Okay. So after the transformer, I have a transmission line whose zero sequence impedance is, how much is the zero sequence impedance of transmission line? J 0.05. Okay. Then again you have one more transformer. Whose primary is star connected and solidly grounded. So I have to open the shunt switch and close the series switch with 3 times the neutral grounding impedance, which is 0. Again you have the equivalent transformer impedance whose value is J 0.07. How the secondary is connected? The secondary side of the transformer is star connected and grounded. So we have to close the series switch with 3 times the neutral grounding impedance, that is 3 into 0.25. So this is your point B, and all neutral ground points are connected like this. So this is your zero sequence network for the given single line diagram. Now he is asking, determine the Thevenin's impedance between point B and the reference. So this is Z0 equivalent. So here, since there is open circuit, we need not consider this portion. All are in series. Very simple. All are in series. So what is the resistive portion? 3 into 0.25. That is 0.75 is the resistive portion. And what is the reactive portion? 0.1, 0.7, 0.05. So it will become 0.22 per unit. So this is the Thevenin's zero sequence impedance between point B and the reference. Gentlemen, have you understood? See, every time you should never forget to write the inductive portions as J, because whenever the resistive portion comes, then you will be in trouble. Resistive portions are real, all the inductive portions are imaginary. You should always precede them with J symbol. Very simple question. I am expecting answer from someone. Read the question and tell the answer. The positive sequence value is 0.03. The negative sequence value is 0.03. The zero sequence value is 0.09. What can be that element? In a transmission line, XL naught is equals to 3 times XL1 or 3 times XL2. and XL1 positive sequence reactance is equals to negative sequence reactance, and zero sequence reactance of transmission line is approximately, it varies from 2.5 to 3.5 times of XL1. So approximately we can take it as 3 times XL1. So this element should be a transmission line. This element should be a transmission line where positive and negative sequence reactance are same. Zero sequence reactance is approximately 3 times positive sequence reactance. Next, see this question and try to answer this one. So here he has given the voltage drops. A three-phase transmission line is as shown in the figure, where the currents are IA, this current is IB, this current is IC. Okay, the voltage drops in the transmission lines are given by delta VA, delta VB and delta VC. So delta VA, delta VB, delta VC is equals to some matrix into IA, IB, IC. IA, IB, IC. Okay, the shunt capacitance of the line is neglected. If the line has positive sequence impedance of 15, the transmission line has a positive sequence impedance of 15 ohms and positive sequence impedance ZL1 or XL1, whatever you think, is 15 ohms, and zero sequence impedance of the transmission line is 48 ohm. Then he is asking, what is the value of ZS and ZM? What is the value of ZS and ZM? Anyone? So we know that in a transmission line, the positive sequence impedance and negative sequence impedance are given by ZS minus ZM, and the zero sequence impedance is given by ZS plus 2ZM. Morning only we have studied this, where we have written in terms of reactances. Here he is giving in terms of impedances. Okay, so ZS minus ZM value he has given it as 15 ohm, ZS plus 2ZM value as 48 ohm. From this algebraic equation, you should get what is the value of ZS and ZM. So if you solve these two, what you are going to get? So if you subtract one from other, so you are going to get 3ZM is equals to how much? 33, which implies ZM is equals to 11 ohm and ZS will become 26 ohm. Okay, so that is the answer. That is the answer. ZM will become 11 ohm, ZS will become 26 ohm. Understood? So this depends upon the sequence networks of the transmission line. Next, try to tell this answer at least.
0.3 and 0.6, sir.
Good, 0.3 and 0.6. Okay, so here excess value is how much? 0.0 ohm per kilometer. XM value is 0.1 ohm per kilometer. So positive sequence reactance XL1 will become XS minus XM, which is 0.3 ohm per kilometer. Similarly, XL0 is equals to XS plus 2XM, whose value will become 0.6 ohm per kilometer. So simple straightforward question where the answer is option D is the right option. Option D is the right option. Understand? So this is GATE 2018 or 19, I don't remember this question. Now try to tell the answer for this one. The series impedance matrix of a short three-phase transmission line in phase coordinates is given by this one. if positive sequence impedance is this one, zero sequence impedance is this one, the imaginary part of Zm in ohm up to 2 decimal places is, yes, tell this answer. What is telling, the positive sequence impedance ZL1 is equals to Zs minus Zm, whose value is how much? 1 plus J10. The zero sequence impedance ZL0 is equals to Zs plus 2 Zm. Please someone mute, it will all recorded. 4 plus J31. So now he is asking first calculate Zm value and tell its imaginary part up to 2 decimal places. Okay. So from this, how you can calculate the Zm value? So if you subtract, let us call this 2 and this 1. If you subtract 2 minus 1, what you are going to get? Zm. 3 Zm will become 3 plus J21. So in this, what is the imaginary part of, so Zm will become 1 plus J10. So he is asking the imaginary part of Zm in ohm, which is up to 2 decimal places, means you have to write 7.00 is the right option. 7.00. You should not even keep the symbol ohm. You should simply write the imaginary part of Zm in ohm. Directly he told up to 2 decimal places. So imaginary part of Zm is 7. Up to 2 decimal places it will become 7.00. That is the answer. This is GATE 2019 question. Okay. To ground fault. Okay. So to understand this one, first we will simulate a LG fault at the terminals of a no loaded alternator. First what we will do, we will consider LG fault at the terminals of no loaded alternator or synchronous generator. Okay. Now if we draw the circuit, how it would be? Okay. Let us consider this is Zn, neutral grounding impedance. Okay. Now, since let us assume the fault has occurred on a phase conductor. This is LG fault. Okay. Now, since the machine is under no load, the currents in phase B and phase C are zero because it is operating under no load condition before fault. Now this is our fault current. Our fault current is equals to IA current, A phase current. Okay. If the fault occurs directly, that means if the transmission conductor or the terminal is directly touching to the ground, if the terminal is directly touching to the ground, it is called dead short circuit. What I'm trying to tell is, if any of the live conductor, either it can be at the terminal of a generator, terminal of a transformer or a transmission line, if it directly comes in contact with the ground, it is called dead short circuit. Or other name is, it is called bolted fault. Bolted short circuit or dead short circuit. Suppose the live conductor is touching the ground through some object, maybe it is falling on a tree, on a wall, or any other terminal box which has some finite impedance. Let us call this finite impedance of that body is ZF. Then it is called a simple short circuit. So there is a difference between a dead short circuit and a normal short circuit. Dead short circuit means the live conductor is directly touching the ground without any element in between. Normal short circuit means the live terminal is touching some body, that body is grounded. It can be tree, it can be wall, it can be anything. So between the live conductor and the ground, there is some body which offers some finite impedance. That is called a short circuit. The other one, where the live terminal is directly coming in contact with ground, it is called dead short circuit or voltage fault. Okay, so here what is our fault? It is a dead short circuit fault. Understand? Now this is normally this is ER, EY, EB. Sorry, not RYB, EAB. We are using international sequence EA, EB, and EC. Okay. So before fault, what are the conditions we know? Since this conductor is directly touching the ground, what is the voltage of this point? The voltage of this point with respect to ground, this is at same potential, so your VA is 0. The voltage of the faulted conductor with respect to ground is 0. So the conditions which we know before analysis, that is preconditions, are what? Preconditions, or sometimes some people call them as boundary conditions. What we know before fault? Our fault current is equals to IA, A phase current, and currents in other two phases are 0 because system is operating under no load condition, and VA value is equals to 0. Voltage of the faulted conductor is 0. Why? Because it is a dead short circuit. Okay, these are the boundary conditions which we know. Now, if you calculate sequence currents, if you compute sequence currents, so original unbalanced currents we know. From this, if we calculate the sequence currents, that is IA0, IA1, IA2 is equals to 1 by 3 into 1, 1, 1, 1, 1, alpha square into alpha into, this is IA. IB current is 0, IC current is 0, so I am substituting their values. So from this, what you are going to get? IA0 is equals to, IA1 is equals to IA2, that is equals to 1 by 3 into IA. That is 1 by 3 fault current. That is the first important result of the LG fault. In a single line to ground fault, all these three sequence currents are same.
Sir,
All the, yes ma'am.
sir, in voltage only the second row will get 1 alpha square alpha, sir. Second row.
No, that is the transformation between the original unbalanced phasors to the sequence system. Okay. So here I am doing inverse.
Inverse, okay.
Okay, understand?
Okay, sir.
See, I have written 1 by 3. 1 by 3 will come in only Z inverse. Yes.
Okay, sir.
Okay. So the first important result which you have to remember in the LG fault is all three sequence currents in an LG fault are same. Okay. All three sequence currents, that is positive sequence current, negative sequence current, and zero sequence currents are same in single line to ground fault. And what is their value? Their value is equal to 1 by 3 times that of the fault current. 1 by 3 times that of the fault current. Okay. Now, the second boundary condition, if you use, what is the second boundary conditions we are having? VA, that is equals to 0, which implies, see, I have told you previously, any unbalanced component in fault analysis, we have to write it as sum of all three sequence components. So VA, I can write it as VA1 plus VA2 plus VA0, that is equals to 0. Okay, so this is also one important result. The sum of all three sequence voltages, the sum of all three sequence voltages, that is the sum of positive sequence voltage, negative sequence voltage, and zero sequence voltage, at the fault point is 0 for a single line to ground fault. The sum of all three sequence voltages at fault point is 0 for single line to ground fault. Okay, so now if I expand this one, what I'm going to get? VA1 I can write from the sequence networks. I can write VA1 I can write it as how much? EA1 minus IA1 into ZG1. Okay, from the positive sequence network of synchronous machine, I can write VA1 as EA1 minus IA1 ZG1. Okay, VA2 how I can write? Minus IA2 into ZG2. This is from the negative sequence network of the synchronous generator. VA0 how I can write? Minus IA0 into ZG0 plus 3ZN. This is from zero sequence network of the synchronous machine. Understand? So from the sequence networks, I can write VA1, VA2 and VA0 in this fashion. So if I add all these three, it should become 0. So which implies EA1 minus IA1 ZG1 minus IA2 ZG2 minus IA0 into ZG0 plus 3ZN. This is equals to 0. But we know what is the first result. We know that IA1, IA2 and IA0 are same for LG fault. So instead of writing IA2 and IA0, I can replace them with IA1. So I'm going to get EA1 is equals to IA1. If I take common, this value will become ZG1 plus ZG2 plus ZG0 plus 3ZN plus 3ZN. Why I am writing like this? Since IA1 is equals to IA2 is equals to IA0 for LG fault. So from this I am going to get IA1 as EA1 divided by ZG1 plus ZG2 plus Z0 where Z0 I am writing it as ZG0 plus 3Z. Every time rather than repeating those things, I am writing Z0 as ZG0 plus 3ZN, which is the equivalent zero sequence impedance of synchronous machine. Equivalent zero sequence impedance of synchronous machine. Okay. So IA0 value I have obtained in this fashion. Now, my fault current is equals to 3 times IA1. Sir, why sir? How sir? So if you go back here, so my fault current 1 by 3 fault current is equals to IA0, IA1 and IA2. So my fault current will become how much? 3 times IA1. So if I write that one, my fault current will become 3 times EA1 divided by ZG1 plus ZG2 plus Z0. So this is the fault current. Understand? Where ZG1 is the positive sequence impedance of alternator, and ZG2 is negative sequence impedance of alternator. Z0 is equivalent zero sequence impedance of alternator. Likewise, you can calculate the fault current. Understand? Now, if every values are given in per unit, if all the values are given in per unit, we can write IF per unit will become So voltage, any voltage per unit values is 1 at an angle 0 divided by ZG1 per unit, ZG2 per unit plus Z0 per unit. So this is the fault current in per unit. Fault current in per unit. Okay. These formulas are used if the fault occurs at the terminals of the alternator. These above formulas are used when the fault occurs at terminals of alternator. Understand? Suppose if the fault occurs not at the terminals of alternator but any point other than the terminals of alternator. Okay, at any point the fault can occur. So for a LG fault at any point in power system network, then what should be the formula? It is very simple. You simply have to write IF per unit will become 3, 1 at an angle 0 means 1 only, 3 divided by Z1 equivalent plus Z2 equivalent plus Z0 equivalent, where Z1 equivalent is the Thevenin's per unit impedance between fault point and reference. Z2 equivalent is Thevenin's impedance between fault point and reference, Thevenin's negative sequence impedance, and Z0 equivalent is zero sequence Thevenin's impedance between the fault point and reference. Understand? We have already computed all these things for different sequence networks, where Z1 equivalent is positive sequence Thevenin's impedance between fault point and reference. Z2 equivalent is negative sequence Thevenin's impedance between fault point and reference. Z0 equivalent is zero sequence Thevenin's impedance between fault point and reference. Understood? Very simple. Just divide with 3 and write the per unit values. You are going to get the IF per unit. Okay. If someone asks you short circuit MVA, again the same formula we have to use. Short circuit MVA is equals to base MVA multiplied by IF per unit. It is same for any formula. Short circuit MVA is given by base MVA multiplied by IF per unit. Okay. So if someone asks you actual current, IF actual will become IF per unit into I base. So base current we have to calculate at the fault location. I base is the base current at the fault location. We have learned that in every section there is one base current. Depending upon the section in which the fault occurred, you have to choose that particular base current value. So very simple LG fault. It is IF per unit is given by 3 divided by ZG1, ZG2 and Z0 in case the fault occurs at terminals of alternator. If the fault occurs at any point, then it is divided by 3 divided by Z1 equivalent plus Z2 equivalent plus Z0 equivalent. Understood? So any doubt in this discussion? Hello?
No.
No. Okay. Now observations of the LG fault. So what are the different observations we have in the LG fault? The first point is, if the neutral of alternator is not grounded, then what happens? See, if you don't ground the neutral of alternator, That means if I remove this Zn, if I keep the neutral open, then what will be Zn value? Your Zn value tends to infinity. It is open circuit. Your Zn value tends to infinity. So when your Zn value becomes infinity, what is the change you see? Here, your zero sequence equivalent impedance, that is Zg0 plus 3Zn, this value, it will become infinity. Why? Because Zn is infinity. Infinity plus anything is infinity only. Your Z0 value become infinity. So when your Z0 value becomes infinity, your IA1 value will become how much? IA1 value will become 0. Your IA1 value will become 0. And likewise, your IF value also will become 0. IF value also become 0. So if the neutral of the alternator is not grounded, what it will become? Your Zn tends to infinity, which implies your Z0, that is Zg0 plus 3Zn, this value also tends to infinity, and your fault current IA1 will become 0, which implies your fault current, that is 3 times IA1, also becomes 0. Fault current also becomes 0. That means if you don't ground the neutral of alternator, then LG fault current is 0. LG fault current is 0. Understand? That is the first observation. That is the first observation. Many people may think, sir, this is an advantage. What is the problem? If I don't ground the neutral of alternator, even though there is LG fault in any one of the conductors, either R phase or Y phase or B phase, then the fault current is 0. What is my problem? What is the problem here? The problem is, if you don't ground the neutral, then you don't know the voltage of the other two phases will increase. The voltage of the other two phases will increase. And how you will detect the fault? Physically, you have to go and see that somewhere it is grounded. Otherwise, you cannot detect that there is a fault. Understand? Suppose if you ground the neutral, so usually how we protect against the LG fault is, you ground the neutral with some impedance and you connect one CT and relay. You connect one relay here. This is called earth fault relay or earth leakage relay. So whenever there is the current through this relay in the reverse direction, that is, what is the fault current? 3IA0. 3IA0 is equals to 3IA1. So how the fault current will flow in the system in case of an LG fault, I am telling you. It starts from the source. It goes through the fault, through the ground, and again through the ground it will enter and it will flow through the system. This is how the fault current will circulate. This violet lines. Understand? So definitely this fault current will flow through neutral for return path. So here the relay will sense the fault and it will trip. So protection is not possible against LG fault if you don't ground the neutral. If you don't ground the neutral, everything, the tripping will happen in millisecond. So you need not worry about this one. So you must ground the neutral of the generator. Why? Because that will help us to detect the fault and rectify the fault. Understand? So neutral grounding must be done to detect and to isolate LG fault. Not only LG fault, even LLG fault also. Okay. So that is the two important points. First two observations. Okay. Next, if the neutral is solidly grounded, if the neutral is solidly grounded, That means if you dead short circuit the neutral, then what happens? Your Zn becomes 0, and your Z0, that is equals to Zg0 plus 3Zn, it becomes Zg0. Okay. So but there will be fault current, the fault current magnitude will increase. So if the neutral is solidly grounded, you have to remember your Zn becomes 0. Zn becomes 0 and your Z0 becomes Zg0. Z0 becomes Zg0. Okay. The third point is voltage of neutral. Voltage of neutral. So voltage of neutral is given by what is the current flowing through the neutral here? The total fault current returns through the neutral. The total fault current returns through the neutral. So since we know IF into Zn, IF into Zn, that is the magnitude of neutral voltage. Mod Vn is equals to IF into Zn. This I can write it as 3 Ia1 into Zn, or most commonly how they write 3 Ia0 into Zn. Why? Because only neutral carries zero sequence currents. So for any fault, the neutral voltage is given by 3 Ia0 into Zn. Since in an LG fault, Ia1 equal to Ia2 equal to Ia0, so we can write in different forms. So neutral voltage is given by IF into Zn, that is 3 Ia0 into Zn. Okay. So if you solidly ground the neutral, then your neutral voltage will become 0. If you solidly ground the neutral, your neutral voltage will become 0. That is one of the advantage of the solid ground. Whatever may be the fault, the neutral voltage will always remains equal to, the neutral voltage always will be equal to 0 volt. That is the advantages of solid ground. Okay. But the disadvantage of solid grounding is the fault current will increase enormously. The fault current will increase enormously. Okay. These are few observations. Next, if you go for next observation is comparison between LG fault, single line to ground fault, and three-phase short circuit fault. Three-phase short circuit fault. It is a comparison between single line to ground fault and three-phase short circuit fault. If you remember our symmetrical fault analysis, the per unit fault current in case of three-phase fault is 1 at an angle 0, that is 1 divided by Z1 equivalent. 1 divided by Z1 equivalent. Or if you consider at the terminals of generator, circuit fault, you write at the terminals of generator. At terminals of generator. Only we are considering the fault at terminals of generator. Then per unit fault current in case of three-phase fault. In case of three-phase fault, the per unit fault current is given by 1 divided by Zg1. 1 divided by Zg1. But in case of LG fault, what is the fault current? 3 divided by 3 into 1 at an angle 0 divided by Zg1 plus Zg2 plus Z0 plus Z0. So this is the fault current in case of three-phase fault. This is the fault current in case of single line to ground fault. Single line to ground fault. Okay. Suppose if neutral of alternator or synchronous generator is solidly grounded. If the neutral of alternator is solidly grounded, that means your Z0 value will become how much? Zg0. Why? Because your Zn is 0. So in this case, what happens? The LG fault current LG fault current will become 3 divided by ZG1. In 99% cases, ZG1 equal to ZG2. So I am writing ZG2 plus ZG0. Because two things here. ZG1 is equals to ZG2. Positive sequence impedance of alternator is equal to negative sequence impedance. And your ZG0 value is very much less than ZG1 and ZG2. Okay. So what happens? For all practical purpose, if we neglect this small value, this approximately becomes 3 times divided by 2 ZG1. It approximately becomes 3 times divided by 2 ZG1. That is 1.5 into 1 divided by ZG1. 1.5 into 1 divided by ZG1. That is, which implies 1.5 into fault current of 3-phase fault. Fault current of 3-phase fault. So what is the crux of this one? Crux of this one, at the terminals of alternator, at the terminals of alternator, if the at the terminals of alternator the LG fault is more severe, because its fault current is approximately 1.5 times that of the 3-phase fault. LG fault is more severe than 3-phase short circuit fault. 3-phase short circuit fault. Many times I get objective question. Okay. At the terminals of alternator, the LG fault is more severe than 3-phase short circuit fault. When the neutral of the alternator is solidly grounded. When the neutral of the alternator is solidly grounded, it approximately becomes 1.5 times. Okay. That is very important point. Next. So we have to continue the same discussion. I am continuing this one. So here, suppose to make LG fault and 3-phase fault equally severe at terminals of alternator. Suppose if I want to make the both faults equally severe, that means I have to equate the both fault currents. Then I have to make IF 3-phase should be equal to fault current of LG fault, which implies 1 divided by ZG1, I should make it equal to 3 divided by ZG1 plus ZG2 plus Z0 plus Z0. So we know that ZG1 equal to ZG2. So to make this one, what I have to make? I have to make the condition your ZG1 should be equal to Z0. This is the condition. This is the condition. So which implies ZG1 should be equal to 3 times Zn plus ZG0. 3 times Zn plus ZG0. If you achieve this condition in a synchronous alternator, then the magnitude of LG fault current and magnitude of 3-phase fault current both are same. So here the equivalent Zn value we require, that is 3 Zn should be equal to Zg1 minus Zg0. Zn will be equal to Zg1 minus Zg0 divided by 3. So a minimum neutral grounding impedance is required, whose value is given by Zg1 minus Zg0 divided by 3. If you ground the neutral of the alternator with this minimum impedance, then your LG fault and 3-phase fault will become equally severe at the terminals of alternator. At the terminals of alternator. That is the crux. Okay. If you ground the neutral of the alternator with this value, then your LG fault and 3-phase fault will become equally severe. Okay. So the moral is, if Zg1 is equals to 3Zn plus Zg naught, then both are IF Lg is equal to IF 3 phase. IF 3 phase. Okay. If Zg1 is greater than 3Zn plus Zg naught, Zg naught here, then IF Lg is greater than IF 3 phase. If Zg1 is less than 3Zn plus Zg naught, then IF Lg is less than IF 3 phase. Okay, so this is the complete comparison between the single line to ground fault and the 3 phase fault. This is the important point. So if there is no neutral grounding impedance, then obviously you can conclude that the LG fault is more severe than the 3 phase short circuit fault. Understand? Okay. Last article in the LG fault is simulation network of LG fault. How to simulate the LG fault? So the two conditions for simulation are in LG fault, all the three sequence currents are same. And the second condition is the sum of all three sequence voltages is zero. So both the conditions must be satisfied. Then how do you simulate a single line to ground fault? How the sequence networks are connected? So first, what is the sequence network? We know positive sequence network of the alternator, which is given by positive sequence network is this one, where this is EA1, ZG1, IA1, and this is VA1. What is the negative sequence network? The negative sequence network of the alternator are this one, where this is ZG2, VA2, and this is IA2. So what is the zero sequence network? Zero sequence network of the alternator is ZG0, 3Zn, this is your VA0, this is IA0. Okay, now we have to connect all three networks such that these conditions are satisfied. So how the interconnection is possible? If you carefully observe, if you connect all of them in series, then you can observe that these conditions are satisfied. So this is how you interconnect this one. Now we can see what is the voltage between this point and this point? 0. This is sum of VA1 plus VA2 plus VA0. This value is how much? 0, short circuit. Understand? Now you see all the currents. What is the current flowing here? IA1. This current is IA2. This current is IA0. So same current is flowing. So unless IA1 is equals to IA2 is equals to IA0, then this connection is not possible, because the same in series circuit, same current will flow. So both the conditions are satisfied. So this is the simulation network of the LG fault. So in LG fault, all three sequence networks are connected in series. That is the simulation of the LG fault. Understand? So gentlemen, let us try to solve this question. Someone read the question.
A 500 MVA 50 Hz 3-phase turbo generator produces power at 22 kV generator is star connected and sir,
It's
its neutral is solidly grounded. Its sequence reactants are x1 equal to x2 equal to 0.15 and x0 equal to 0.05 per unit. It is operating at rated voltage and disconnected from the rest of the system. The magnitude of
subtransient.
Magnitude of subtransient line current for single line ground fault at the generator terminal in per unit
will be very simple, straightforward question is asking. So first he has given one generator. There is one generator. So all the data of that generator is given. At the terminals of generator, LG fault occurred. That is the story. So before fault, the generator is under no load. Before fault, generator is on no load. Same as the conditions which we used for our derivations. Okay. So what is the voltage of the generator? 22 kV. What is the MVA rating? 500 MVA. Okay. Now the positive sequence reactance, he gave x1, x2, x0. We use the notations ZG1, ZG2 and ZG0. So ZG1 is equals to ZG2 is equals to 0.15 per unit. J you have to put, and ZG0 value is equals to J 0.05 per unit. How this alternator is grounded? It is solidly grounded. So the grounding of alternator is, it is solidly grounded. So your Zn is 0. Zn is 0. That is the concept. First we have to calculate the per unit fault current. Per unit fault current in this case is how much? 3 divided by Zg1 plus Zg2 plus Z0. Understand? So since your Zn is equals to 0, which implies your Z0, that is equals to 3 Zn plus Zg0, this value will become equal to Zg0. Understand why? Zn value is neutral, is solidly grounded, so your Zn value is 0. So if you substitute these values, you are going to get 3 divided by the positive sequence impedance is 0.15, J 0.15, J 0.15, and Z0 value is J 0.05. Since we only want the magnitude, we can ignore those J's. So you are going to get 3 divided by 0.35. So this is the per unit fault current. So what is the per unit value? Someone tell this one. So actual fault current is given by per unit fault current multiplied by base current. Okay. So this value is how much? 3 divided by 0.35. Someone should tell it. 2 point. So this value will become 3 divided by 0.35 is the per unit current. Base current is given by, already we know base current formula, IB is equals to S base divided by root 3 V base. Since we have only machine ratings, we have to substitute them. 500 MVA divided by root 3 into 22 kV, so many kiloamperes. So if you get this value, this is the fault current that flows immediately after 7 per unit. So this is the right option. But if he asks the actual fault current also, then we have to multiply with the base current, whose value, base current value is given by S base divided by root 3 V base. That is 500 MVA divided by root 3 into 22 kilo. So this will give you the actual fault current in kiloampere. Understand? So this is the option 8.553 per unit. Yeah, a very lengthy question, but very easy answer. So here what he's telling, at 20 MVA, someone mute themselves. At 20 MVA, 6.6 kV, three-phase alternator is connected to a three-phase transmission line. Okay. So he's telling an alternator is connected to a three-phase transmission line. Understand? The alternator is grounded through a reactance of 0.05 per unit reactance. Okay. The alternator rating is 20 MVA, 11 kV. Okay. And the positive sequence reactance of negative sequence and zero sequence reactance of alternator Zg1 equal to Zg2 equal to J0.1 and Zg naught value is given by J0.04
Sir,
per unit.
20 MA 6.6
Sorry, ma'am, 6.6
generator.
kV. Yes. Voltage is 6.6 kV. Okay. So here he gave a generator is connected to transmission line, and at the far end there is a single line to ground fault, LG fault occurred. So this is a transmission line. He gave that the neutral of the alternator is grounded through a reactor of inductive reactor of J0.05 per unit. He gave the positive, negative and zero sequence values as these values. Now he gave the positive, negative and zero sequence reactances of transmission line are, that is ZL1, ZL2 values are J0.1 and the zero sequence reactance value is J0.3. Okay, all per unit values are based on machine ratings that is 20 MVA and 6.6 kV. A solid ground fault occurs in one of the phase at the far end of transmission line, then the voltage of the alternator neutral with respect to ground is. So at the far end of transmission line, a single line to ground fault is occurring. Now he is asking what is the voltage of neutral with respect to ground. So what is the formula for voltage of neutral? This is IF into Zn, IF into Zn, or 3Ia0 into Zn. So to calculate the voltage of neutral, you need to compute the fault current. In first step is we have to compute the fault current. So to compute fault current, since if there is a generator only, we could have directly substituted the formula. But here two elements are connected. Two elements are there. So for that you have to draw the positive sequence network, negative sequence network and zero sequence network for each of them. Okay. For the given network, if we draw the positive sequence network, so how many elements are there? There are only two elements. First element is generator, whose reactance is this one, and then a transmission line whose reactance is there. So at the far end of transmission line, fault occurred. So this is the fault point. This is 1 at an angle 0. Positive sequence impedance of generator is how much? Zg1 is 0.1, ZL1 is also J0.1. So this value is J0.1, J0.1. This is neutral or ground. Reference for positive sequence network is neutral or ground. So if you calculate the Thevenin's impedance, that is Z1 equivalent value, you're going to get this value as J0.2. J0. So that is the positive sequence Thevenin's impedance. Similarly, if you draw the negative sequence network for the same system, so it is exactly same as positive sequence network, but before that you have to check once whether for a synchronous machine Zg1 and Zg2 are same or different. So here they are same, so you need not worry. So it's going to become again J0.1, J0.1. This is the fault point. This is the neutral or ground. So there are no induced EMFs in negative sequence network. So this Z2 equivalent will become same as J0.2 per unit. J0.2 per unit. So if you draw zero sequence network for this system. Now first you have alternator. Whose neutral is grounded through a reactor whose value is J0.01. So Zn value is J0.05. So your zero sequence network will become 3 times Zn, and this is Zg0, and again you have a transmission line, this one. So this is ground. So 3 Zn value is 3 into 0.05, that is J0.15. This is J0.04. This is J0.3. So this value is Z0 equivalent. So this value will become how much? 0.49 per unit. Okay, this is 3 Zn, this is Zg0, this is ZL0. Since there is no transformer, there is no complexity in the connection. So you know Z1 equivalent, Z2 equivalent and Z0 equivalent. So formula for the fault current in single line to ground fault, IFLG is given by 3 divided by Z1 equivalent plus Z2 equivalent plus Z0 equivalent. Okay. So for any point, for any fault point in LG fault, we have to compute the Thevenin's equivalent impedances which we have computed. So directly 3 divided by all the sum of all three Thevenin's impedances. So it will become 3 divided by 0.2. If I want only magnitude, 0.2 plus 0.49. So if you compute this magnitude, what is the per unit fault current? 3.37 per unit. Your IF per unit is 3.37 per unit. Now, what is the voltage of neutral? The voltage of neutral is IF into Zn. IF value we have computed 3.37 into what is the impedance of neutral? J0.05. So 0.05. If you only want to compute the magnitude, your neutral voltage is 3.37 into 0.05. This value will become 0.168 per unit. 0.168 per unit. So, but he's asking the actual value. So for actual value, remember this very important point. Vn per unit into phase to neutral base value. You should not multiply with the line to line base value. You have to multiply with the phase to neutral base value to get the voltage of the neutral. Okay. So 0.168 multiplied by line to line base voltage is 6.6 kV. Phase to neutral base voltage will become 6.6 kV divided by root 3. So this is your exact neutral voltage whose value comes out to be 642.2 volt. So this is the voltage of neutral with respect to ground. So normally you calculate Vn per unit value and multiply the Vn per unit with the phase to neutral base voltage. You are going to get the actual neutral voltage with respect to ground. Okay. So when the fault occurs at different location, first you have to draw the positive sequence network, negative sequence network, zero sequence networks, calculate the Thevenin's equivalent impedance between fault point and reference, then substitute in the formula. This is how you have to do this kind of problems. Okay. Now, read this question. Severity of line to ground fault and three-phase faults at the terminals of unloaded synchronous generators is to be same. If the terminal voltage is 1 per unit, Z1, Z2 values are Z0 values are given, then the required inductive reactance for the neutral grounding is what he's telling. I want to make the severity of single line to ground fault and three-phase short circuit fault equal at the terminals of alternator. Then what is the per unit inductive reactance that have to connect between the in the neutral of the alternator? So for this we have done all the analysis and we derived at one conclusion. What is that? If Zn is equals to, that is 3Zn plus Zg0, if it is equal to Zg1, then both the fault will become equally severe. So from this you are going to get Zn is equals to Zg1 minus Zg0 divided by 3. So if you ground the neutral with this much of impedance, your LG fault and three-phase fault are equally severe. So here he gave Zg1 value means Z1 value is J0.1, G0 value, that is Z0, that is value is J0.05 divided by 3. So this is the reactance that is with which you have to ground the neutral. So this value will turns out to be J0.00166 per unit. So option A is the right option. So you have to ground the neutral with this much amount of reactance so that both faults will become equally severe. Okay. Now, for a fault at the terminals of synchronous generator, the fault current is maximum for which fault? For the fault at the terminals of synchronous generator, the fault current is maximum for line to ground fault. Which is the most severe fault at the terminals of generator? LG fault. Okay. So C is the right option. Remember this point. We have already proved this one. So at terminals of generator, if data is not given, blindly if you ask the question which is the most severe fault at the terminals of synchronous generator, LG fault is more severe. LG fault is most severe at the terminals of alternator. At all remaining points in power system network, three-phase short circuit fault is What are the three-phase short circuit faults? Triple L and triple LG are most severe. Understand? Only at the terminals of generator LG fault is more severe. With remaining all location, three-phase short circuit fault is most severe than any other fault. Understand? Remember this point. Read this and tell what is the right option. 1 and 3 is the right option.
Option B.
Option C. So option C is the right option. Okay. So in the neutral grounding impedance appears as 3Zn in the zero sequence equivalent network. Yes, it is true. The neutral grounding impedance appears as 3Zn in the zero sequence equivalent circuit of the synchronous machine. That is true. Now see, for the fault on transmission line, the three-phase fault is least severe amongst other fault. No. For any point apart from generator terminal, the three-phase fault is most severe. That only we have discussed. For any point in the power system, at all remaining points in the power system network, the three-phase fault is the most severe. So second statement is the Wrong statement. This is wrong. So since the fault is in transmission line, the three-phase fault is the most severe fault. Again, the positive and negative sequence networks are not affected by neutral grounding. Why? Because either in positive sequence network or negative sequence network, the neutral voltage and ground voltage both are same, they are zero. So neutral grounding does not affect positive and negative sequence network, which is true. So which is the right option? Out of which are the following are correct? 1 and 3 are the correct. 1 and 3 are correct. So next, read this question. So this is the last question for today, and then we will close the session. Okay. Tomorrow again we'll have class at 10, where we'll complete the complete fault analysis. Okay. So at a 220 kV substation of a power system, it is given that the three-phase fault level is 4000 MVA and single line to ground fault level is 5000 MVA. Neglecting the resistance and shunt susceptance of the system, the positive sequence driving point reactance at the buses and the zero sequence driving point reactance at the buses. So two questions here. This is linked type question. So what he's telling, at a 220 kV substation bus bar, at a 220 kV substation bus bar, the short circuit MVA of three-phase fault is 4000 MVA. The short circuit MVA of single line to ground fault is 5000 MVA. Okay. So now he is telling what is the positive sequence Thevenin's impedance and what is the zero sequence Thevenin's impedance between fault point and reference. Okay. Now for this, very simple. Let us take a tabular column. First we'll write three-phase fault. Second side we'll write LG fault. So here short circuit MVA is, he has given how much? 4000 MVA. Here short circuit MVA for the fault at the same location, he has given this value as 5000 MVA. Okay. But I know what is the formula for short circuit MVA? Base MVA into IF per unit fault current. Here also the formula is same. Short circuit MVA is equals to base MVA into IF per unit. If you remember the base MVA formula, if you recollect your per unit system, how we can write the base MVA? Z base is equals to, if you remember the formula for Z base is equals to VB square divided by S base. Understand? So from this, how I can write S base I can write it as base voltage square divided by Z base. I will write S base using this formula. Okay. This I am taking from the per unit system which we have learned. So short circuit MVA is equals to base voltage square divided by Z base into what is the per unit fault current in case of three-phase fault? 1 at an angle 0 divided by Z equivalent per unit. Z1 equivalent per unit. Positive sequence Thevenin's impedance. Here short circuit MVA is given by, again I am using the same formula. Base MVA I am writing it as VB square divided by Z base into, here what is the formula? 3 into 1 at an angle 0 divided by Z1 equivalent per unit, Z2 equivalent per unit plus Z0 equivalent per unit. That is for the per unit fault current at any point for LG fault. Okay. Now if you see, Short circuit MVA value is 4000. What is the bus bar voltage he has given in the formula? Bus bar voltage is 220 kV substation. So our bus bar base voltage should we have to take it as 220. So it will become 220 kV square. 220 kV square divided by 1 into 1 means 1 only. Z base multiplied by Z1 equivalent per unit. So base value multiplied by per unit value you are going to get Z1 equivalent actual value. Z1 equivalent actual value. So positive sequence actual value will be given by, if you cross multiply, 220 kV whole square divided by 4000 MVA. kV square and MVA will cancel. So what is the value you are going to get if you substitute in this one? 220 square divided by 4000.
12.1.
So this positive sequence Thevenin's impedance is 12.1 ohm. 12.1 ohm. So the positive sequence driving point reactance is 12.1. Option D is the right option for the first question. Now he wants the zero sequence Thevenin's impedance. How we are going to get that? Again here the short circuit MVA is 5000. That value is equals to again 220 square into 3, because here 3 is there, divided by Z1 equivalent, sorry, here Z base into, so Z base multiplied by the all per unit values. So it will become the actual values, that is Z1 equivalent plus Z2 equivalent plus Z0 equivalent actual value. Okay. So if you want this actual value, you are going to get Z1 equivalent plus Z2 equivalent plus Z0 equivalent actual values is equals to 220 square into 3 divided by 5000. So what is this value? If you do the calculation, 20 square, 4. But we don't want all the value, we want Z0 equivalent. We know that most of the cases Z1 equivalent is equals to Z2 equivalent. Both values are same. So if I substitute the Z1 equivalent and Z2 equivalent value from here, I am going to get 12.1 plus 12.1 plus Z0 equivalent actual value is equals to 29.04. So from this Z0 equivalent value I am going to get it as 29.04 minus 24.2, 4.84 ohm. 4.84 ohm. That is the zero sequence Thevenin's impedance for this one. Zero sequence Thevenin's impedance 4.84 ohm. That is the option B is the right option.